Around 300 BC, Greek geometers developed an entire mathematical system and achieved amazing results using only two simple tools, an unmarked straight edge and a compass. But the solution to three problems eluded them. They were trisecting an angle, doubling the volume of a cube, and squaring the circle. It was not until the 17th century that a formal proof demonstrated the impossibility of trisecting an angle. But, as so often happens in mathematics, the pursuit of a solution led to many fruitful discoveries. In approximately 200 BC, a man named Nicomedes devised a method of trisecting an angle, but it relied on what is known as a higher-order curve. That is, a curve that cannot be constructed using only the classical tools, an unmarked straight edge and a compass. The curve became known as the Conchoid of Nicomedes. Back when Nicomedes constructed his curve, it would have been rather cumbersome and he might have needed the help of some patient friends. Nowadays, we can conduct mathematical explorations much more easily with the help of technologies such as Geometer's Sketchpad. Let's use Sketchpad to explore this famous curve. Let's start with a point and call it the pole. Next, a line called the directrix. This line is the asymptote of the conchoid. Let's represent the distance from the pole to the directrix as the radius of a circle. Notice that Sketchpad will allow me to change the distance from the pole to the directrix just by changing this radius. Now a second circle. The endpoints of a diameter trace the locus of the curve, but with one important limitation. This line must pass through the pole. Thus, although the distance from the pole to the curve may change as the line swings, the distance from the directrix to the curve remains constant along the line through the pole. Let's trace our conchoid. Notice that this distance is changing. It's the distance from the curve to the pole. But notice that the radius of the large circle remains the same, so the distance from the directrix to the curve is always the same. Notice the classic loop underneath the pole. The conchoid is a family of curves, and let's show a couple possibilities. Let's see what happens to our curve if we make the radii of the two circles the same by changing the bigger one and trying to make it exactly the same as the smaller. Can't quite get close, I'm a pixel off, but let's highlight the two endpoints, display a trace on the intersections, and see what happens to the curve. Notice that when the diameters are the same, we've lost that attractive little loop at the bottom, and instead the curve is just cusping at the pole. We've got one more possibility. What happens if the distance from the pole to the directrix is greater than the radius of the green circle? Now our third possibility. Let's make the green circle smaller than the red circle and see what happens to the curve. Once again, highlight those endpoints, trace the curve, and let's animate. Notice that now we've not only lost the loop we had at the beginning when the green circle was larger, we've also lost the cusp. And as the ratio changes, the two loci of the curve are getting more and more like straight lines. Now that we know how to construct a conchoid, how do we use it to trisect an angle? Well, the first step is to let the swing line create an angle such that the short red line CP is exactly 1/2 the length of the long red line AB. So CP is equal to half the distance from the directrix to the curve. Once we have created this relationship, we have established an angle that can be trisected using this particular conchoid. So the first step in our proof is to take that point C and construct a perpendicular to the directrix going from C to point F on the curve. Take point F and use it to draw a line through the pole. Remember that any line that passes through the pole has the same length from the directrix to the conchoid. So the red line AB is the same length as the blue line FG and the same length as the blue line DC. Now we find a midpoint of the blue line FG, we'll label that M, and we draw a line back to the directrix at point C. Because CP is also half of AB and half of FG, we know that we have lots of segments that are the same length. MF, MG, and CP are all the same length. Notice that we've created a right triangle, and because of the properties of right triangles, we know that not only are MF, MG, and CP the same length, MC is also the same length. We also know that since that's a right triangle, we've created two isosceles triangles within here, and because CP is the same length, there's a third isosceles triangle, this pink one. This is important in looking at the relationships. First of all, we know that these two lines AB and FC are parallel and they're cut by the transversal. Thus, the alternate interior angles are equal, and we also know that this angle in the pink isosceles triangle is an exterior angle, and an exterior angle is equal to the sum of the two remote interior angles. Because in this case the remote interior angles are of an isosceles triangle, they're the same. So we know that this angle CMG is exactly twice the angle CFM. Furthermore, since we know that this angle and this angle are the same in that they're base angles of an isosceles triangle as well, we know now that angle MPC is twice angle CFM. We're just naming these angles differently. We know that MPC is the same as FPD. We know that CFM is the same as CFP. And since this angle, FPD, is twice this angle CFP, we know that by substitution, FPD is twice angle APF. And thus we have proven the trisection of the angle. Let's remove some of these other triangles so we can see clearly. The yellow area, APF, is exactly 1/3 the area FPD, and our angle is trisected. I cannot emphasize enough that this trisection was possible only because of the relationship between the red line CP and the other red line AB. That creates the angle APD that is able to be trisected by this particular conchoid. If you wish to trisect a different angle, you need to construct a different conchoid.